So at this point, I'm going to turn the evening over to Rick Costello, who is, he says, a long-term enthusiast about the stars and the universe. He became interested way back when the astronauts first landed on the moon. I can remember that night. I bet most of you can too.
Yep.
So at this point, let me turn the microphone over to Rick.
Thank you, everyone. Nice to meet you. Can anybody hear me without the microphone, or is...
Please use it.
Use it? Okay. Use the microphone? Okay. Everybody hear me fine? Well, thanks everybody for coming here. Nice to see everybody here. Yeah, I've been studying the universe basically since the day I could read. I always wondered, remember as a tiny kid looking out my car window, looking at the stars, going, what are those things? And since then, I've just had to understand the universe, and I spend most of my life, all my life, trying to understand it and learning. And now I do a bunch of telescope shows for the public and private in different schools and groups and stuff, and it's kind of like my life now, teaching and showing people the universe. And so we'll get started here. Basically, when I do my telescope shows, I find a lot of people don't understand, where we are in the universe and in the galaxy and other galaxies. And this talk, I'm going to kind of talk about where we are in the universe. And we begin with, of course, our home planet here, the planet Earth. And the planet Earth is about 7,924.5 miles in diameter. This one's a little squashed for some reason in this photograph, but and it's basically our home, our spaceship in space. And on this next slide here, let me just move this over a little bit. Yeah, here we go. We're basically call us a water world, but this is like how much water and air we have on the planet. The average depth is about 2 miles, and that's about the amount of water and air we have on our planet. And luckily enough to sustain life for us. And here we're going to start moving away from the Earth. We think this is a gigantic planet, but it's, like I say, it's a little less than 8,000 in diameter. And as we move away, this is a shot from the Apollo era, one of my favorite shots of the Earth. And here we are with the lunar lander coming back up to the module in the Apollo days. And the Earth is smaller and smaller. And here's a shot of the opposite side of the moon. And the opposite side, it's all craters. There's no the lava plains on this side of the moon. There's none of that. It's basically just millions of craters on the other side of the moon. And as we move further away, we get to the distance between the moon and the Earth. And the moon's about 30 Earth diameters away from us, 239 miles on average. It goes out to, it's not a complete circular. It goes out to 251,000 and comes in as close to 228,000 miles of us. And if you notice, you'll notice at points the moon is larger in the sky and then smaller, and that is as closest and furthest distance away from us, and that's why that happens. And here we move even further away from the Earth, and this is a shot from a few million miles away, a shot of the Earth and the moon, and then we get to this shot here, and this is from the Voyager. This is the Earth from 3 billion miles, and as Carl Sagan said, he looked at this picture. He called this, we are just basically a speck of dust in the universe, our planet, and a lot of space between us and everything. And so this is a Voyager from a picture of Earth from 3 billion miles away. And this next one, we get to the sun. Oops, there we go. And the sun, if you see the sun's white, the true color of the sun is pure white. If you're out in space, it's pure white. We see a yellowish star because of particles in our atmosphere refracting off. The light refracting sends off an orange or yellowy sun for us. But in space, it's actually a white sun. And this is our sun, the surface of the sun. And the surface is about 10,000 degrees Fahrenheit, and basically the surface of the sun is basically you think of almost like a pot of water, a boiling pot of water. And the sun is made of a plasma, and the plasma means normal atoms, they'll have the nucleus of the atom and the electrons orbiting the nucleus. The plasma means that the electrons have been flown off, and that usually is caused by high temperatures, and it's very hot inside the sun. So basically, the free electrons mean that's what a plasma is, when the electrons are free and not orbiting. And so it's basically a giant plasma ball, our sun, and you see some of these flares here, these magnetic fields. And the sun is basically, basically a giant ball of gas, a plasma gas. And these things here, if it was a normal color, these would probably be one of the dark spots on the sun. And basically magnetic fields, and you can see some of the protons and neutrons that make up the sun following the magnetic fields. And these magnetic fields, they have a north and a south side, a positive and a negative side. And sometimes they touch each other. When they do, that's when a solar flare will just send a bunch of solar material out into space, and that's what a solar flare is. Basically, when the magnetic field, the north and south poles hit each other, and that will cause the explosion and send some of the surface. Which is part of the solar wind. The solar wind, it's not a wind; it's actually particles. It's basically protons, neutrons, and electrons. Basically, what atoms are made of. Now we get to the interior of the sun here. And the sun has basically three features. It's got the core, and right now the core is about 26 million degrees. And at that temperature, the atoms are moving really quickly, basically hydrogen and hydrogen, helium, hydrogen with one proton and helium with two protons, and is a mass majority of the sun, but in the core, the hydrogen is actually smashing together and fusing atoms to make a helium, and also giving us light. And then you have the radioactive zone here, and this is a really thick, compacted plasma. And when the light is created here, the gamma rays, it'll take up to 500,000 years for that light to travel through the radiation zone. And that's because the photons that are created from the core, it's really packed, so it takes a while to get out of the core. When it gets to the radiation zone, the protons and neutrons, electrons that are in there, the photons will run into them, be absorbed, and then they'll be shot out again, and you never know what direction they is. Sometimes they go back to the core, sometimes they go up. So basically a light is almost like a pinball machine, where the photons come up a little bit, they get absorbed by a proton, and they shoot out, go down, and they kind of do this. And then 500,000 years later, they'll finally reach the edge of the radiation zone. And then the convection zone, which is like boiling water. It's heated from the bottom above the radiation zone here, and then it's basically just like boiling water. The heat rises to the surface, cools, and it sinks. And the light will take about a month to travel through here, and once it gets to the surface, the light will travel 8 minutes, a little over 8 minutes to the Earth. And it's a good thing this light takes a long time to leave us here. And I'll just show you the process that's going on in the sun with the nuclear fusion. And it's basically fusing hydrogen into helium at a rate of 600 million tons per second. And it's been doing that for 4.5 billion years, and it'll continue doing that for another 5 billion years. And so here, both these you see are the same thing. And this is what's happening when we want to end up with a helium atom here with the red 2 protons and the gray two neutrons here. And on both sides here, you see you have 2 protons here, and they smash into each other, and it releases a positron, which is the opposite of the electron, and then also a neutrino, which is a small, almost massless particle. And right now, those neutrons that are leaving the sun, every inch of you right now are billions and billions of these neutrinos going right through us. They go right through the Earth like nothing's there. They don't even notice us. And then so you end up with 1 proton and 1 neutron, which is a heavy hydrogen, deuterium they call them. Most of the water on Earth has just 1 proton and electron, but this is a heavy hydrogen. Some of the water in the ocean does have this heavier hydrogen here. So you end up with that, and then another proton comes around, they combine, they fuse together, and you release a gamma ray, and that's the light that we're eventually going to see, the gamma ray. And then you end up with a 2 proton and 1 neutron here, and that's helium, but with only one proton, a neutron, I'm sorry. And then you end up here on the other side, 2 of these, and these smash together, and they release one of the protons each, and then you end up with a 2 proton, 2 neutron stable helium. And basically that's what the sun's doing at a rate of 600 million tons per second, and then 4 million tons of that 600 million tons, it releases energy as gamma rays. And like I said, when these gamma rays are formed, we're lucky that it doesn't shoot right out of the sun at us and reach us 7 minutes, 8 minutes later, because they'd be gamma rays, and it would just toast our atmosphere away. We'd be an unlivable planet. But luckily, it takes 500,000 years for that light to get out of the sun, and it kind of slows down its energy, and it becomes infrared visible light and ultraviolet light, and that's the light that leaves the sun. And here we go back to the planets here. It's kind of the size of the planets here to each other. You see the distance from each other. You know, the farthest planet, Neptune, almost 3 billion miles away from us. And here, you know, then we got Neptune, or I'm sorry, Uranus, you know, 17,000 million, or you know, 1.7 billion miles away from us. So this is pretty far. And the reason they stay orbiting the sun is because of gravity. And Isaac Newton, he thought that gravity was something like the moon, that the Earth was pulling it on the moon, and it was keeping the moon in orbit. And then Albert Einstein came along, and he said, no, gravity is actually the bending in space. And you can picture, like, say if I had 4 people in a blanket, and I had everybody pull that blanket really tight at 4 corners, if I put a ball in the middle of that, it would cause that indent. And where that ball is, it would be an indent around that ball, too. And that's what gravity is. And the planets are basically following that indent around the sun and the moon around us. And that's what gravity is. And so gravity is actually the bending of space. And then we get here, we've got the planets here. We got the planet Mercury. And Mercury's got a diameter of 3,032 miles. And a little bit bigger, it's about a third bigger than the moon is. And it's 58 million miles from the sun, and it's basically, it kind of looks like the moon. It's you know, if you can see the interior, there's actually a really large core in it compared to the other planets. And they think from this picture, the core would be, you know, if we could see, it'd be about this big inside there. And they think Mercury might have been a much larger planet, but being so close to the sun, being hit by the solar wind, the particles from the sun, the protons and neutrons and electrons, that Mercury actually has a tail behind it where the surface is being blown off by the sun. And they think over the last 4.5 billion years, Mercury has been slowly and slowly getting smaller and smaller, losing its crust. And then we go on to the next planet, the wild planet of Venus. Venus is, Venus has a 7,500 mile diameter. And when you look at Venus, it's basically, it's just all clouds. When you look through a telescope, it's just a shiny kind of yellow ball. And it's thick clouds of carbon dioxide and then sulfuric acid, which is otherwise known as battery acid. And that's what the clouds are made out of. And go to this next one. It shows the surface of Venus. It's basically the surface is really young from volcanic activity. Basically, a lot of volcanoes, hundreds of actually thousands of volcanoes on Venus, and over time, it's basically resurfaced the whole planet. And so we got a really young planet. And here's a shot of the surface. This is a shot from the 1970s from the Russian Venera craft, which landed on Venus, and it lasted about 20 minutes before it was crushed in the heat. And you notice all the rocks are flat here. And that's because, besides the temperature being over 800 degrees, and that's because of the carbon dioxide, and we talk about our global warming with carbon dioxide forming a blanket where it lets the light in, but doesn't allow the heat to escape from space later, warming up the planet. Venus has a runaway greenhouse effect, where the temperature is over 900 degrees Fahrenheit, and the surface temperature, or the surface pressure, where on Earth, if I took a square inch and I made a column all the way to a square inch column all the way to the top of our atmosphere, the atmosphere would weigh 15 pounds on our shoulder, every square inch. On Venus, it's 1,500 times, or 1,500 pounds per square inch. So anything on Venus is just going to be crushed. And not a very hospitable place. Actually, Venus, I made a mistake there. It's actually 1,350 pounds per square inch. And so that's just the weight of the atmosphere on top of anybody who's on the surface. And that's why the rocks here are all flat, because of that pressure from the atmosphere, the weight of the atmosphere. Then we get to the planet Mars, the red planet. Now Mars has a diameter of about 4,200 miles, and it gets its red color from iron that's in the rocks, in the sand, and the iron is oxidated, it's basically rusted, and that's why they call Mars a rusty red planet, because the iron is actually rusted. And here we have a canyon here, and this is Valles Marineris. It's 2,500 miles long, it's about 120 miles wide there, and up to 4 miles deep. And to give you an idea of just how large this is, that's it compared to the United States. And somewhere right around there is the Grand Canyon, you know, which is our Great Canyon, but just a huge canyon there. And then we go to this next slide, the largest, well, I should show you here. Also on the side here, we have these three volcanoes here on the side here. And this next one is actually just on the other side here out of this picture. And this is Olympus Mons, the largest volcano in the solar system. And it's, you know, Mount Everest is 5.4 miles high. This volcano is 13.6 miles high, and it's 380 miles wide. So just a gigantic volcano here. Dormant though, it hasn't erupted in hundreds of millions of years. And then we go to the next planet out, a distance of 484 million miles away from the sun, averaging. And Jupiter's 88,000 miles in diameter. And inside, this is an older picture of Jupiter in the red spot here. In this older picture, you can actually fit 3 Earths inside there. But in the last few years, the red spot has actually been shrinking, and now it's down to the size of about 1 Earth, and they think it may be disappearing. So it's getting smaller and smaller. And then and Jupiter's and Saturn also are made just like the sun. They're basically giant balls giant balls of hydrogen and helium, mostly hydrogen. And it's also got other heavier elements. And these orange clouds here, that's actually phosphorus that's high in the atmosphere. Gives us that red color. And this storm here, this has been spinning since at least Galileo saw it almost 400 years ago. So it's well over that. And if Jupiter being just a ball of gas like the sun, these clouds move in different directions. Some are moving this way, some moving this way. And what keeps us rotating is this cloud here is actually moving in this direction, and underneath this one's moving this, so it's kind of moving like this, and it keeps that circulation going. But it seems to be slowing down. And on the poles, it's just beautiful. It's almost like a piece of art. This is the southern pole of Jupiter. So some great cloud patterns there. Next, we move to the planet Saturn. And we go, and Saturn's got a diameter of 74,000 miles, almost 75,000. And the rings here, they extend from about a little over 5,000 miles. There's some rings in here that you can't see, but they extend about 5,000 miles out to about 75,000 miles. And now these rings, they're basically made of ice particles, some rocks, but mostly water ice, and probably moons that got too close, and the gravity basically tore them apart. And the sizes range from just tiny flakes to maybe the size of a average, a $250,000 house. How's that? About that. But mostly small particles. In these rings in this coming November, there's another picture of the rings there. Just a beautiful planet to see through the telescope. And come November, the rings are going to be edge-on to us, which happened 11 or 12 years ago, and the rings are going to disappear for a few nights, and then it'll start opening up again. So right now, Saturn is kind of closing. In November, they're going to be edge on to us. And edge on to us, the rings are only about 40 feet thick, which is amazing when you think. Basically, maybe from me to the wall, that's about as thick as those rings are. Some pieces are a mile high, but the vast majority of the rings are basically within 40 feet thick, which is pretty amazing when you think about it. But from ice world. Most of the moons in our solar system are made of water ice, and other things too, but mostly water. And then here we are, Uranus, at a distance of 1.7 billion miles. Incredible. It's got a diameter of 31,700 miles, and it's mostly made of, like Jupiter and Saturn, mostly of hydrogen and helium, but it's also got methane and ammonia in its interior, and it's actually, the interior are actually rocks, and then the methane in ammonia water. I'm sorry, methane and ammonia ices. And they called Uranus and Neptune ice worlds because there's a lot of ices in that. And there's a picture of Neptune here. Now both these colors get their, planets get their blue colors from methane. And methane in the upper atmosphere, it absorbs all the colors except blue, and it lets blue escape. So we see these two planets as blue as the methane absorbs all the other colors. And yeah, Neptune, the farthest planet, takes like 169 years to orbit the sun, from a distance of 2.8 billion miles. So when you get to Mars, Mars is about a little over 50 million light years away, or 50 million miles away from us. Then you get to Jupiter, it's almost a half a billion. You get to Saturn, that's a billion and a half, almost 2 billion miles, or I'm sorry, a little under that. You get to Uranus and Neptune, 2 billion and 3 billion. So basically, from Jupiter, Jupiter and Neptune, the planets basically double in distance. Get to almost 3 billion miles for Neptune, which is incredibly far away when you consider each of those billion is 1,000 million miles. And then we get to our last, oh no, it's not a planet anymore. Sorry, everyone. But yeah, this is a planet, Pluto. There I go, I made a mistake. The dwarf planet, Pluto. And this is a picture of the New Horizons craft that went by it a few years ago. And Pluto's got a diameter of 1,473 miles, pretty small, and basically a dwarf planet. And as we look past Pluto into the Kuiper Belt, we're actually finding these other, there's 3 moons out there, dwarf planets are actually close in size to Pluto. And as we look into the Kuiper Belt, we'll probably find more of these size small planets, or whatever you want to call them, dwarf planets. And yeah, let's see here. This next one is a picture of the Kuiper Belt. Now, once you get beyond the orbit of Neptune, you run into the Kuiper Belt. And I should say our solar system is basically flat. You can think of our solar system almost like an old record, where the sun's in the middle and the planets on different grooves. And if you watch the planets go, move through the night sky, you'll notice they all follow the same path in the sky, and that's because the solar system is basically flat. And then you get to the Kuiper Belt, and that's still on that flat plane. And the Kuiper Belt, it goes out to about 80 AU. 1 AU is about the distance between the Earth and the Sun. So you figure about 100 million miles for each AU, a little less than that. And this one's about 80 of those away from us to the outer extensions. And then we get to the Oort cloud. And here the Oort cloud basically surrounds us. And it's basically a circular thing all around us. And our solar system would be this thing in the middle here. And here are just filled with probably millions and millions of comets. I mean, they're pretty far from each other. They wouldn't be so dense as it's shown here. But this thing basically surrounds our whole solar system and extends halfway to the nearest star to us. And then we move out to the galaxy. And our galaxy is basically stars and gases and dust. And in our galaxy, they estimate anywhere between 300 billion to 400 billion stars in our galaxy. And there's another photo here of a star cluster. I mean, there's millions and millions of stars in this cluster here. And this is looking towards the center of our galaxy. And these other star clusters I like, they're called globular clusters on this next one. And these things are very old stars. These stars range from 10 to 12 billion years old. And they sit above our galaxy, like the solar system, is basically a flat disk. And these things kind of sit above and below the disk. And there's like 150 of these globular clusters. And this is a Hercules globular cluster. And it's about 150 light years across. But in there's about 400,000 stars. And there's some of these that have millions of stars. But very old stars. There's another globular cluster there. And when I move to our galaxy here, our galaxy is basically flat. And these things sit above and below. The Hercules globular cluster is right over here in Hercules. And so this is basically what our galaxy looks like. This is basically a flat, but this side would connect to this side and this side to this side. So this kind of wrap around us. This is a flat view of our whole galaxy. And And you see all the nebula here, the clouds of atoms that'll be forming new stars. And then we get to Alpha Centauri. The closest star to us is this star right here, the one on the left of these two brighter ones. And you can only see that from the southern hemisphere. But Alpha Centauri is 4.2 light years away from us, which equals about 25 trillion miles to the closest planet. And here's a photograph of the closest planet, right there, Proxima Centauri. And it's a small red dwarf star. It's got about 12% of the sun's mass. And these red dwarfs, where our sun will last for about 10 billion years, these red dwarfs will last for trillions of years, probably over maybe 1 to 2 trillion years before they use up their hydrogen fuel. And then up here, what looks to be 2 stars, this is actually, Proxima Centauri is part of a 3-star system. And here's an image of these 2 other stars, are pretty close in that other image. And these stars are a little bit more massive than the sun. This one's 1.5 times the mass, and I think this one's 1.7 times the mass. So a little bit heavier than our star. And then we go back here. That's there. Yep, and we got, over here on the right, we have the Orion Nebula, or Orion constellation. You see the 3 stars of Orion's belt there. And here we look at here. And this is up in the southwest sky right now. One of my favorite constellations to look at a telescope. But these 3 stars of Orion's belt are just massive stars. You have the one on the left here, Alnitak, that's about 1,200 light years away from us. And it's got the mass of 33 of our suns. Just a huge star. It's got a diameter. The diameter is about 20 times the mass of the sun. And it's a super blue giant. And it's about a little over 6 million years old. And these 3 stars will live for 7 or 8 million years before they go supernova. And then you have the one on the right here is Alna Lam, and that's a little over, it's 1,280 light years away, a little bit further than Alnitak. And Alna Lam I'm sorry, the one on the right is Mintaka, a little messed up here, but yeah, Mintaka, 1,200 light years away, 1,280. It's got the mass of 24 of our suns, another blue giant, a diameter of 24 times the mass of our diameter. Then you get to the middle star here, which is Mintaka, which is one of my favorite stars. This is a supermassive star. And it's 64.5 times the mass of our sun. Just a humongous star. And it's, again, a blue supergiant. The diameter is about 80 times that of our sun. And our sun's a little less than 1 million miles in diameter, 884,000 miles in diameter. And this one's 84 times that. And about 6 million years old for that one. So these are all massive stars. And each one of these is going to blow up in a supernova in their lives. And this one being 33 times the mass, 64 times the mass on Mintaka, those are probably going to leave black holes when they're done. And then you have the middle one here, probably going to end up as a neutron star. And when stars, any star over 8 times the mass of our sun usually ends its life in a supernova. And if they're 8 times to 24 times the mass of the sun, the core will collapse into a neutron star. And if they're over 25 times the mass of the sun, they'll collapse into a black hole. And so, yeah, the 2 stars in the end there are going to end their lives in black holes. And then we get to the star. Let's see here. Yeah, then we go here to. We go back here to Orion. Oh, I think I went the wrong way here. It's there. Yeah, these are some of the sizes of stars. The sun here, barely see it. You get the Betelgeuse, and that's 600 million miles in diameter compared to our sun, which is 884,000 miles in diameter. And you get larger and larger skies, and here, UY Scuti is the largest star so far in size, not in mass, but as far as size. And it's 1.47 billion miles in diameter. And again, our star is less than 1 million miles, so it's just a humongous star. And if we could put the sun next to this star, that's how big the sun would be next to this star. And if you put one edge of this star where our sun is, at the center of the sun, the outer edge would almost reach the Uranus. That's how large that planet is. That's a humongous star. Now the largest planets, these are the ones that make us and make planets, and these stars, we owe these stars. And what's happening, where our star will fuse the hydrogen to helium, and then the core will crush, and right now I said the temperature is about 26 million degrees. At that point, it'll crush the core and build up the temperature to 100 million degrees, and then that helium will start fusing into carbon and oxygen, and it'll end up with a carbon and oxygen core, and then that's about it for our star. But these massive stars, they start fusing, and the fusion starts going, and it ends up almost like an onion where you get different layers of different atoms here. And eventually, when the core turns to iron, that's as far as the fusion is going to go, because you need temperatures in the trillions of degrees to fuse iron, and that can't happen in a star. And eventually, there's two things going on in a star. One part of it is that the heat is pushing the star outward, and gravity's pulling the star inward, and it keeps its shape by, they call it equilibrium, it keeps its shape. But once the core turns to iron, the push outward from the heat is going to grow less and less and less, and eventually it's going to reach a point where gravity's pull inward is going to be stronger than the push outward from the heat. And when that happens, the core in just a split second is just going to crush down to 11 miles if it's a neutron star, or to a pinpoint if it's a black hole. And then the whole outer layers, and so you have the core here, and you have the outer layers here, and when the core collapses, all the outer layers come rushing in, the inner layers bounce off, and you end up this, and that creates a shock wave going through the star, and that creates temperatures in the trillions of degrees, and that fuses all these other elements up to the element uranium with 92 protons, the heaviest element. It forms everything, all the calcium in your bones, the iron in your bloods, the oxygen we breathe, the magnesium, everything that makes us, the silicon in the rocks, came from exploding stars. And if it weren't for exploding stars, the universe would remain only hydrogen and helium, which are created in the first second of the Big Bang. So if it wasn't for these giant stars that blow themselves up, creating all the elements, there would be no planets or anything besides the hydrogen and helium. So we owe our existence to these giant stars. And here, back to Orion's belt, that's what I show you. This, underneath it, you see these, there's three dim stars, but the one in the middle is actually the Orion Nebula. And there's the Orion Nebula. It's about 26 light years across. Again, the closest star to us is 4.2 light years, so it's pretty big. And inside this cloud, it's collapsing, and thousands of new stars are being formed. And here's a couple pictures of some stars being formed, new solar systems. They call this protostars, so they're just starting out here. And there's another one here. But if we can get this is an artist's rendition of it, but if we can get close up, this is basically what it looks. You have the protostar growing here, and you have this massive, all the elements to make everything. And in this mass, planets are being formed, as well as collapsing and growing the star in size. And so that's what a new solar system starts out as. And then one more thing to show you here, off this last star here, is the Horsehead Nebula, and you'll actually see this star and the second star in this shot, which are right there, and that's where the Horsehead Nebula is. And the Horsehead Nebula is about 1,300 light years away from us, and it's actually further than Alnihat attack there, which is 1,200 light years away. And the Horsehead is a close-up of it right there. And that's what the Horsehead is, just a giant. And these are nebulas, these clouds of atoms. And they're just, all the elements to make everything are in there. And eventually they'll collapse to form new stars, and now stars and planets. And as we go back here, let's head towards our galaxy again. And our galaxy, basically, I said, a flat disk. Zoom in here a little bit to the center. But you see a lot of these nebula clouds here, these dark clouds. Mostly hydrogen and helium, but again, through supernova, a lot of heavy elements here. And we go to the very center, you see the cloud right there. And yep, and then just another thing, this is up in our summer sky, located right there. And you've probably seen pictures of this. This is the Eagle Nebula. And then inside there, you have the Pillars of Creation, which you probably recognize that photo from the Hubble. And from here to here is about 4.5 light years. And so the closest star to us would be like from here to there. I'm sorry, this is 7 light years long. So the closest star to us would be like, from there to there. Just to show you how huge these are. And this is the Webb telescope view, and Webb uses the ultraviolet light, which actually sees right through the clouds. And so you can see some of the stars being formed in there. Again, another giant star-forming cloud. And that's what these nebulas are. These nebulas are all throughout our galaxy, and they're all star-forming clouds, a lot of them, and some young stars being formed in this cloud. And this is the Ring Nebula here, another nebula. And this is what's going to happen to our sun. Like I said, our sun's going to fuse hydrogen to helium and helium into carbon and oxygen. And when it starts fusing the helium into carbon, you know, the temperature goes up to 100 million degrees. That extra heat is going to cause our sun to expand into a red giant. And the outer edges may reach the Earth. I mean, Mercury and Venus are definitely going to be inside the sun by then. And eventually the sun gets so big, it expands so much that the gravity from the core can't hold on to the outer layers of the sun, and the solar wind kind of just blows them off. And that's what you see here, is a smoke ring kind of thing. And that's the outer layers of that star being blown away. And here's another one here. And inside here is a star, and this star is a white dwarf star. And that's the remaining core of the star, and I guess the outer layers. And this is the same thing that's going to happen to our sun in about 7 billion years from now. There's another one there, a star losing its outer layers. And these things are just beautiful, almost like pieces of art. And again, I said the core will be a white dwarf. And it's basically a big ball of carbon, electrons, and neutrons, and oxygen. And that's about the size of it. White dwarf would be about the size of the Earth. And that's what's going to happen to the core of our sun eventually. But the massive stars, they completely blow themselves up. And they'll leave either a neutron star or a black hole. And this is a Crab Nebula. And again, this is just, within this dust, this gas and dust are all the elements to make planets and everything. And so these are what we need to survive. Another supernova remnant there. And then we get to our galaxy. And now our galaxy is pretty much a flat disk. Let me see here. And yeah, if you can see the galaxy from the side view, if we could be out of our galaxy, that's kind of what our galaxy would look like from a side view. Now, if you're going to look over the galaxy from the top of it, this is what our galaxy would look like from above. And we're located right here, about 26,000 miles from the center of the galaxy and about 25 from the outer edge. And our galaxy is about 100,000 light years across. You know, if you could travel the speed of light, it would take you 100,000 miles to cross. And just to explain a light year, if I had a giant flashlight and I pointed up in the sky and I measured how far that light traveled in 1 year, it would travel 5,900,000,000,000 miles. But we rounded off to 6 trillion, and what's 100 billion when you're that close to it? So almost 6 trillion miles light travels, and it would take you 100,000 years across this. And it's basically our galaxy, a two-armed spiral galaxy, and it's got a couple galaxy arms here, and like I said, we're located right here. And basically all the stars that we can see in our sky are about this far away from us. That was about all the stars that we can see when you look up in the sky. The rest of the galaxy, those stars are too far to see with our eyes. Now this is another galaxy which we think our galaxy very much looks like. This is a real galaxy, very similar to what our galaxy looks like. And then it's basically a spiral galaxy. And now our galaxy, you know, it takes us, well, if I go back to this picture here of our galaxy, it takes us about 225 million years to rotate around the galaxy one time. And we go around the galaxy kind of like a carnival horse, a merry-go-round horse, where right now we're above about 52 light years above the plane of the 1,000 light years thickness of our galaxy. And we're actually going up, and as we go around the galaxy, we'll go up to about 250 light years above the plane, and then we'll come down past the plane to about 250,000 light years. So we kind of go like this around the galaxy. And it takes, like I said, about 225 million years to go around the galaxy one time. And in the 4.5 billion years since our solar system has been here, we've gone around the galaxy about 18 times. And again, this is a picture of another galaxy that's very similar to ours. And these are just some more galaxies here, some spiral galaxies, very similar to ours. And basically, galaxies are basically just collections of stars or gases and dust which make stars, and that's what they're doing here. And now less than 100 years ago, the people living at that time, they thought when they looked up at the sky that our Milky Way galaxy was the only galaxy in the universe. We thought this was the whole universe. But we can see these very misty things in the sky. There's another one over here. And in 1926, Edwin Hubble was looking at the Andromeda galaxy, and through his 100-inch telescope at Mount Wilson in California. And over in this area here, he noticed a Cepheus star, which is a star that expands and contracts at a usual pace. And from there, they can determine the distance. And Hubble, he estimated that Andromeda was 1 million light years away from us. And it turns out it's 2.5 million light years. But he discovered other galaxies, and all of a sudden the universe got larger. At the time, they thought our galaxy was the only one in the universe. Oh, did I miss that? Let me see here. Maybe I did. Yeah, there's another picture of the Andromeda galaxy. And like I said, the rest of the universe, as we move out into the universe, is galaxies. And this is what's going to happen to the Andromeda galaxy and our galaxy in about 5 billion years as they move towards each other. And these two galaxies are colliding. And they'll kind of slide past each other, then gravity will pull them back, and they'll do this dance for a few billion years. And eventually they'll join to form a larger galaxy with the mass of both those galaxies. And that's how galaxies get larger over time. And then over here, in the southern hemisphere, you can see these two faint misty patches here. And those are two smaller satellite galaxies, the large and small Magellanic clouds. And there's a close-up of them here. One of my two favorite galaxies to look at through this telescope. You've seen these, Steve. We've looked at these. And these are about 12 million light years away. And then the galaxies just keep getting further. The rest of the universe is just all galaxies, each their own collection of tens of millions of stars, hundreds of millions, billions of stars, and some galaxies with trillions of stars. And there's a nice spiral galaxy. These are nice spiral galaxies, a bar spiral like our galaxy because there's bar here, but basically just a giant rotating disk of gas and dust. And we got the Whirlpool galaxy, which is right off the last star of the handle of the Big Dipper. There's actually a second galaxy here, which is messing around with this galaxy. But this galaxy is a little bit, about half the size of our galaxy. And then we have here the Sombrero galaxy, which is up now. It's about 50 million light years away from us. And there's about a trillion stars in this galaxy, and you see the flat plane, the nebulas, and the gases and dust in it. And we just, like I said, the rest of the universe, just galaxy after galaxy. Another spiral galaxy here, another galaxy here, and the Black Eye galaxy here. And this is up in the sky right now. And here's another galaxy. You see the black hole at the middle is shooting out these jets. And what happens at the center of every galaxy are these massive black holes. The center of our galaxy has a black hole 4 million times the mass of the sun. Andromeda has about 20 million times the mass of the sun. And some of the black holes can be billions of times the mass of the sun. But as things get close to the black hole, they fall right into the black hole. They usually start orbiting it. And when you start orbiting the black hole, the closer you get, you start going faster and faster and faster. And as you get closer, you get close to the speed of light just before you dive into through the event horizon, which I'll explain in a second. So what's happening, this stuff is spinning around the black hole, and the magnetic fields cause these jets to shoot some of the matter out from the black hole, and that's what these jets are here, shooting the mass out of there. And these are a couple of my favorite galaxies to look at. These are up now in Virgo, the Markarian chain. These galaxies are part of the Virgo cluster. And we're part of the Virgo cluster. There's a long chain of galaxies that you can see up in the sky now in the east when it gets dark. And there's about a couple thousand galaxies that we're part of. And we're kind of all gravitationally bound together. And most of the galaxies I've shown here are the spirals. We see some of these elliptical galaxies here. There's some of the ellipticals, and these are the most massive galaxies. These galaxies can have trillions and trillions of stars, and they're basically, they've been formed by just the colliding galaxies that made the galaxy larger and larger and larger, and not flat at all. And we get into the deep space here, and we're looking at galaxies. This galaxy is here about 5 billion light years, and we get here about 8 billion light years. But as we look back in time, you notice how these galaxies are closer and closer together. And here we are here with some more galaxies. And as we look back in time here, yeah, just more galaxies and more galaxies in the universe. Two stars in this one. And then we get to the Hubble Deep Field. And the Hubble telescope stared for, I think it was like 1 million seconds or 1 million minutes or something like that, whatever it was. And it basically stared at one spot near the Big Dipper. And if you took a grain of sand and held it at arm's length, that's how much of the sky this picture is. And there's about 10,000 galaxies in here. These galaxies, about 9 billion light years, but these smaller ones are up to 13 billion light years away from us. And you see the universe, when the light left these galaxies, 8 to 13 billion, or 9 to 13 billion years ago, the universe was a lot smaller back then. It was maybe a third of the size it is now. And so, NASA will say, yeah, we're looking at these galaxies 13 billion light years away. That's kind of a misnomer, because we're not actually seeing them as a distance, because the universe was a lot smaller back then, and say the farthest galaxy was, say, 8 billion light years away from us. And for the last 13 billion years, the universe has been expanding, so it's taken that light 13 billion years to finally catch up to us. So we're seeing these galaxies actually as a time 13 billion years ago, and not so much as a distance. And that's the great thing about telescopes or time machines. As we look further and further away from us, we're looking further and further back in time. When I look at the moon, I look at the moon and see how it looked 1.2 seconds ago. When I look at Jupiter or Saturn, I see Saturn as it looked an hour and a half ago. It's taken that light that long to reach us. And this light has taken billions of years to reach us. So we're actually looking into the past. And that's the great thing about telescopes, is the further we look in the past, if we look at galaxies 13 billion light years, 12 billion light years away from us, 11, 12, all the way closer to us, we can actually see how the universe aged. We can watch the universe age. And that's the great thing about light, because it has to travel to us, so we can actually see the universe as it looked 13 billion years ago, which is how we get our information about it. And this is one of the farthest galaxies they've seen. I think this one's 13.4 billion light years in the past, one of the earliest galaxies that they've seen. And when you get to what space is, they think matter, they think this dark matter. We can sense dark matter's gravity. As the galaxies are spinning, but they're spinning faster than they should be. The outer stars should be flung out of these galaxies, but by the speed that they're spinning. But what they think is that the galaxies actually has 70 times more mass, or 70% of the mass is actually dark matter. Or it should, like Neil deGrasse Tyson says, it should be called dark gravity, because we don't know what it is, but we can sense its gravity. And they think space is just like a web of all this dark matter, and then the normal matter will be attracted to the web, and you see the galaxies on this web of dark matter. And if you really study the galaxies, like kind of this one's here, this one's here, this one's there, you find out they're kind of on this web throughout the universe. And they have no idea what dark matter is. They know it's there. They think it could be possibly a massive particle that we just can't notice yet. Or it could be, they think it could be maybe another universe on top of us where the gravity's seeping into our universe, which is just bizarre, but they don't exactly know where the gravity's coming from with dark matter. And then we get to the very edge, and this is the farthest we can see in our universe. And this is the microwave background radiation. And this light is light from 380,000 years after the Big Bang. When the Big Bang happened, it was thousands of trillions of degrees. And then when the Big Bang universe expanded quickly, the temperature dropped from thousands of trillions of degrees in 1 second down to 10 billion degrees. 3 seconds it dropped to 1 billion degrees. And that huge drop in temperature basically turned the energy into matter. Einstein's E equals mc squared, which means matter and energy are basically the same things, just different forms. And so when the temperature dropped, those particles of energy froze into particles called quarks. And there's different kind of quarks, but two types are up and down quarks. And when you take 2 up quarks and 1 down quark, you form a proton. When you take 2 down quark and 1 up quark, it forms a neutron. And within the first minute of the universe, all the neutrons and all the protons in the universe were created to form everything. And then you know, they formed either 1 proton, which is hydrogen, or 2 protons, which is helium. And that was basically the whole universe. A little lithium with 3 protons. It was basically, so this light, before this, the universe was so hot, it was a plasma. It was, you know, pretty dense with material. So just like being inside of a star, the photon couldn't travel more than a centimeter at most before it ran into an electron, which likes playing with photons. They don't let them travel very far. So the light could only travel a few centimeters, and you never know which way it's going. And so light couldn't travel any further. And then about 380,000 years after the Big Bang, the temperature dropped to about 5,000 degrees. And at that temperature, the nucleus of the atoms were finally able to capture the electrons. When they captured the electrons, the light was finally able to travel the universe. And this is the light that we see. And this is actually the light from the Big Bang. And you see the different color variations, but it's only it's pretty uniform in the temperature. There's only 1 part in 100,000 difference in the temperature of the universe. And a lot of these these red spots here, that's where the matter is, the cooler spots here, and eventually those will turn into the galaxies. This is basically a picture of our universe 380,000 years after the Big Bang. And if we go back far enough, this was that was too quick. If we go back far enough, the universe was just a speck, tinier than an atom, and all the energy of the whole universe was in there. There's no matter, just all energy. And then all of a sudden, boom, boom, we'll go this way. And then the universe was created. But I should explain in this one, when you look at this, there is no outside here. The whole universe is in that tiny little spot. There's no outside at all. And then when the universe created, it also created space. So that's there. And so that's pretty much our universe from the Big Bang. And the Big Bang created protons and neutrons, which created helium and hydrogen, helium, more in that order, and a little lithium. And then from there, the stars took that helium and formed heavier atoms, which formed planets and water and everything that we can breathe and everything in us, everything in rocks. And so without the supernova, it'd be impossible for us to be here. So we owe our existence to stars. So that's basically the universe. And if you just go backwards, it's just all the way back at 13 billion years of time. And it's incredible when you think 13 billion years, how long that is, that the universe is here. When you think 13 billion years, each billion is 1,000 million years. And the universe, they're estimating to be 13.7 billion years old. And just a incredible amount of time. By the time our solar system formed 4.5 billion years ago, our universe was already over 9 billion years old at that time. And we're kind of late in the game here, I guess. And so you have stars, much older than us and billions of years older, and then there's always the question of is there life in the universe? And my thought has always been, if we're here, it proves that life is all over the universe, because all the ingredients to make life is everywhere we look. And carbon-based life is probably most life. Is carbon binds with so many different other atoms. And so, my guess is eventually our government's going to come, oh yeah, we're not alone. I hope that happens in my life, because I know we're not alone. When you figure there's 400 billion stars in our galaxy, and almost every star when you look in the sky has planets. There's trillions and trillions and trillions of planets in our galaxy alone. And then you have 2 trillion other galaxies, each with hundreds of billions of trillions of stars, each, and quadrillions of planets, or probably quintillions of planets throughout the universe. And so my dream in life is that they announce that there's life out there. I would just love that. It would just be a special day for humans to knock us off that pedestal. No, we're not the only ones, but someday that's going to happen. Hopefully in our lifetimes, I would love to get that news that we're not the only ones. So that's the lecture. I hope you enjoyed it, and if you have any questions, Yes?
You were saying that our universe is expanding.
Yep.
Why is it expanding?
The question for Michael is, why is the universe expanding? They're not sure what, they call the expansion dark energy. And it's basically expanding. And the way the universe expands is for every 3.26 million light years, the universe is expanding about 42 miles an hour. So if I look at a galaxy 3.2 million light years away from us, it's expanding us about 42 miles per second. Now if I look at a galaxy twice that, it's moving twice that speed away from us. If I look at a galaxy 3 times away from it, it's moving 3 times further. If I look at a galaxy 100 times further away from it, it's moving 100 times faster. If I look at a galaxy 1,000 times further away, it's moving 1,000 times faster. And then by the time we get to the edge of the universe, it appears those galaxies are moving faster than the speed of light because of that. But they're moving just as fast as we are. But the space between the galaxies is expanding. And they're not sure why that's what dark energy is, but they know it's happening. The universe is not only expanding, it's speeding up. It's getting faster and faster and faster. And right now, their estimate is that within like 50 billion years, the universe will expand so fast, it's going to break everything apart. That even the planets are going to be ripped apart, the atoms with us are going to be ripped apart, the whole universe will be torn apart. And possibly in 50 billion years. But so they're kind of hoping that something counteracts it, or maybe it weakens and it slows the universe down. Because some theories say that the universe will speed up and eventually it'll slow down and then it'll contract and come back to each other to another point, and then that'll cause another big bang. So you get this, this repetition of, universe is expanding, contracting, and And there's other theories to the universe where there was actually a larger Big Bang. And this thing happened, could have been infinity ago. And as it expands, you get these little pockets where you get a universe here, a universe here, a universe here, a universe here. And as it expands, it keeps making more and more universes. And they think that could be possible. Or they think in our universe, the expansion, the Big Bang and the expansion is still going on in our universe. And in our universe, you'll get different pockets where the physics are different. So you basically get different universes springing off that. Yeah, so in the math that the quantum physicists are doing, it's kind of showing that, other universes pop out in their math. They're not sure if that's true or not, because we can't prove if there's other universes out there, just for the fact that the light never have time to reach us. So there could be other universes out there besides our one universe. Do you have a question? Yep.
You were telling us how long it takes to go around our galaxy.
Yep.
And how many times we've done it.
Yep.
What do you mean by going around the galaxy?
Well, if I... Oh. Yeah, sure. Maybe. Let me just move up to the quicker like this, I guess. A lot of pictures in here. There we go. Yeah, I'll take this galaxy here. Oh. Yes, I'll go back to that one to us, since that's more like ours. Yeah, so basically, this is basically almost like a flat pancake. It's 1,000 light years thick, 100 light years across. And it's basically rotating. We're moving around the galaxy about 600,000 miles an hour, our solar system. And we're moving in this direction. It takes us about 225 million years to go around the galaxy one time. Yep. Yeah, this whole thing is turning. Yep. Yep. Yeah, we just keep rotating. We've gone around the galaxy about 18 times in the last 4.5 billion years. Yes?
So when you showed the picture of just the Big Bang,
The dot.
one kind of thing,
Yep.
since at that particular instant it also created space, right?
Yes.
So actually, the Big Bang occurred everywhere.
Yes. Yeah. People ask, where's the center of the Big Bang? It's everywhere. Because everybody was in that center at one point, the whole universe. So basically the center of the universe is everywhere. The whole universe was, you take an atom, it was smaller than the nucleus of an atom, just packed with pure energy. you know, and then it expanded, and when it expanded, it created space. You know, there's nothing outside that dot. You know, but you know, and they know the universe was once at a point, because if you look at all the galaxies, if you played all the galaxies in reverse, they'd all come together at the same point, at the same time. And so they know that at one point the whole universe was in a point. So they know the Big Bang happened, and you know, basically they understand a trillionth of 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 a second after the Big Bang. It's just that first little couple quadrillions of a second that they don't understand, because the temperatures are thousands of degrees, thousands of trillions of degrees, and so our math just breaks down. We're not sure what happens in that first trillions, couple trillions of a second. Yeah. You're welcome. Yep.
Okay, back to the Big Bang. I got a couple questions. Back to the Big Bang thing.
Yeah, I'm going to bring it over just so Mike can record this.
Like, you know these particle accelerators that they have
Yeah.
around the world?
Yeah.
They say they're trying to create like the Big Bang atmosphere.
Yeah.
I mean, temperatures or something. How do they learn from that?
Okay, what they do is, it's all magnetics in there, so the magnetics make the particles go in a circle.
Yeah.
And that one's 17 miles in diameter. In 1 second, the particles go around about 11,000 times, because they're traveling almost the speed of light. You know, in 1 second, light will travel around the Earth 7.5 times. You know, if I go one, light's been around the Earth for 7.5 times. You know, and so basically, they send them that speed, and then they crash the particles together, which creates, and when they crash them together, the constituents break out. You see all the different things, just different things coming out of that. And it creates really high temperatures, and they can break the particles apart and see what they're made of. You know, and basically that's what they're doing.
So it helps them understand the Big Bang somehow.
And particles, yeah, because they're trying to figure out, you know, what makes an atom, what makes a, you know, atoms are made of protons and neutrons, electrons. Protons and neutrons are made of quarks, and you know, that's a fundamental particle. String theorists will say the quarks are made of vibrating strings, and there's 11 really tightly wound dimensions in there, but unprovable. That's their problem right now.
Here's my second question. We got all these galaxies out there, right?
Yep.
And we can see them well.
Yep.
And you have great pictures of them all. We can see pretty far, you know, billions of light years or millions of light years out, right? How do we know what our own looks like, really?
Well,
because we're in the middle of it.
Yeah. Well, up until a couple of years ago, we thought our galaxy was a four-arm spiral. But with different telescopes, especially the infrared, because the infrared can look right through all the clouds. You can see right to the center of the galaxy. They've actually seen stars orbiting our black hole. They'll come really slowly, and they get near the black hole, they'll speed up really quick to like 9 million miles an hour. And then they'll slow down, they kind of do this. And what was your question? I'm sorry, I was kind of got lost in that.
How do they know what our galaxy
Oh,
looks
yeah.
like, because you're in the middle
Yeah,
of it?
well, that's
Kind of like you're in your car looking out the windows.
Yeah,
right?
yeah. It's very much like that, because you know, the galaxy's 1,000 light years thick. We're 52 light years above the plane of that, and we're trying to understand the galaxy by looking through the forest, almost.
Right.
You know, these clouds are in the way and all these stars, but now with these new telescopes, it's starting to see, you know, like we know on this side of the galaxy, we're here, there's a small galaxy actually entering our galaxy right now. It's crashing into our galaxy, a small dwarf galaxy. And we didn't know that 5 years ago, but these new telescopes let us see through farther, because it looks right through the nebula, the clouds of atoms. But we're not 100% sure what our galaxy looks like.
Yeah, I mean, how do we even detail what the boundary is? Like what I'm saying is, I guess by the motion, you see these stars moving around with the rotation you mentioned.
Yep.
And then the other ones are not. So they're further out, maybe in another galaxy.
Yeah.
I don't
Well,
know.
yeah. Well, a lot of times they look at the star, and if they can tell what type of star it is, from the temperature of the star, they can tell where it is in its life cycle, so they can guesstimate the distance. Yeah.
All right,
And
thanks.
yeah. Any other questions?
Yeah,
Sure.
supernova event coming up, whatever
Yep.
it's called, the star that periodically explodes every 80 years. I thought a supernova, when it exploded, it was over and done with.
Yeah.
But this seems like, you know,
Yeah.
oscillating kind of event.
Yeah.
So can you talk about that?
Yeah, supernovas are when they just blow themselves up, and
Right.
when the core turns to iron and it collapses and blow up. A nova is a pulsating star. Like our star towards the end of its life will probably become one of those, where you get blasts from the center, and it'll blast things off the outer layers. You know, like this picture. Was it? Maybe up. Yeah, kind of like this picture here. You know, it's kind of like pulsating off. So they can, yeah, they can tell a lot of information about the star that way.
Yeah.
Yeah.
So,
yeah.
so that's supposedly going to be so bright. Right now, you can't see it with the naked eye, but it's going to be so bright
Yeah.
that
Yeah.
you can see it with the naked
Yeah.
eye. Are you going to be having
I'm-
viewing parties?
I'm hoping to go.
That?
Yeah, I'm hoping to check that out.
Okay.
There's actually a comet too out in the west right now. It's supposed to
Right.
be visible to the naked eye. Yeah. Yeah. So that's basically a pulsating star, and it's basically throwing off the outer layers, and those will light up, and that's what you'll see.
So it's a nova, not a
And yeah, that's a nova.
Okay.
Yeah. Yeah.
Okay.
Yeah. Yeah.
I've heard discussion lately about speed of light,
Yep.
and you cannot exceed the speed of light.
No.
So the distances that we're talking about, just within our solar system, let alone our galaxy, are such that even though each one of these stars now they're establishing, there are planets around all these stars.
Yep.
And you're talking about there's got to be more people like us around there, maybe not like us,
Yes. Yeah.
but the reason we are not able to interact is because of this distance
Yeah.
and the speed of light constant.
Yeah.
But is there a way that you can overcome that? You know, like,
I mean, we could travel 99.9% of the speed, or even 99.99% of the speed of light. But the problem with light is, like Einstein says, relative. So no matter what speed I'm traveling at, light is still moving 186,000 miles per second. So if I'm traveling at half the speed of light, and I measure light, light's still traveling 186 miles per second. If I'm traveling 99.9% of the speed of light, and I measure this, light is still traveling away from me at 186,000 miles per second. So, and the way that works, the faster you move, the slower time gets. So say if you're here and you're moving faster and faster, time gets slower and slower. The faster you get, time gets slower and slower. Finally, you reach the speed of light, time stops. And so like these galaxies, the light that left those galaxies billions of years ago, say 13 billion years ago, the moment it left that galaxy 13 million years ago, and the moment it strikes a telescope 13 billion years later, is the same exact moment to that photon.
okay,
Yeah, if you could travel the speed of light, you'd watch the universe age. It would just go, woo, 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 woo. You'd watch billions of years pass by you. Yeah, yeah. Is that all your question, or did I answer it? Okay. You're welcome, thanks. Yep, anybody else? Yep. I'm gonna come back there just so Michael can,
I'm not sure I want it on a microphone.
oh, please. You're-
I don't even know how to put this into words, but like, how do you think about where it ends, or how it does end, or how it doesn't end, or how it begins? Like the whole everything. I don't even know what you call it.
Yeah, are you looking for a purpose?
My personal purpose. That's been my whole life.
Yeah,
But
yeah.
no, I'm just trying to think about how do I think about it.
Yeah. I mean, how do you,
And if you're not a particularly religious person,
yeah, yeah.
how do you even conceive of what, you know,
I find it easier to be non-religious, to look
Okay.
at this stuff than to be religious.
really?
Well, the religion, a lot of them says the whole universe is 6,000 light years old. You know, and I'm looking at galaxies that light take 13 billion years.
Yeah.
You know, but how do you think about it? How do you
Yeah, how
put
do
it?
you- I
How
mean,
do you
how
put
do
it in
you, like-
perspective? I don't know, because I mean, sometimes I can just sit there, close my eyes, and you know how you get in that fog where you're just like, why is there anything at all?
Yeah.
Why are we here? How did we get there? Why is there planets? Why is there air? Why is this? I mean, I don't know what to think. I mean, for me, I love thinking about it. I love knowing that the universe is billions of years old. I mean, you know, we're lucky if we get 50, 60, 70, 80, maybe 100 years of life. You know, and our planet has been here for 4.5 billion years. You know, and each billion years is 1,000 million years. And when you get to that time, I mean, I don't know what to make of it in that sense. To me, it's wonderment. you know, that much time has happened, everything that's here, that, you know, stars make, you know, turn hydrogen into all the other elements that make us and planets. It's just pretty amazing, but how to put that all into perspective and go, yeah, I'm not sure, I guess that's a personal thing. Yeah, yes?
I would suggest that's why they made scotch.
Yep, yeah, scotch, that's right. His comment was they made scotch because of that. And I agree with that, yeah. Yes?
So it's kind of back to her question, I think, too. I mean, I think the hardest thing to conceptualize is that, like you say, the universe is expanding. It's kind of like a balloon that's going bigger and bigger and never pops.
But the skin, only the skin of the balloon, yeah.
It has to be infinite because what's on the other side?
Yeah.
Is that dark matter or dark matter, or whatever you're talking about?
Well, I mean,
it has to be infinite because there's always another side.
Yeah, I mean, say if my microphone is our galaxy.
Yeah.
We have a 13 billion light year cone around us that we can see. Now, if you're at this galaxy 13 billion light years away from us, they probably have their own 13 billion hole. And if you go to this galaxy 13 billion light years away, they probably have their own 13 billion light year cone. So we have no idea how far the universe goes. But most likely, if you're at that other galaxy, you're seeing the universe just as as we do. If we look this way, we see galaxies 13 billion light years away. If we see that direction, 13 billion light years away. So every galaxy would have its own 13 billion light year cone around it. You know, so most likely the furthest that we see, if you went to those galaxies, you just see more galaxies beyond that.
So it's just infinite.
It could, yeah, our universe could go on infinitely. We can only see it as far as light has traveled to us. Right. You know, 13 billion years, a little over that. So it's as far as we have no idea what's beyond that. Just most likely more galaxies. But then you make it further and further away, and also the physics may change. There may be no galaxies. There may be no atoms, you know.
Right.
But then there could be more. There could be even more bizarre stuff.
I heard you talking about multiverse before, which is the topic of all these latest sci-fi movies the last couple of years. Right?
Yeah.
Multiverse.
Yeah, and but you know, it's there in the math. But how do you test it? And that's why a lot of astronomers are like, you know, it looks really good on paper, but we can't test it. We'll never, you know. Who may never be able to test it, you know? And like you were saying with life in the universe, I mean, we look at us as being smart, and it's like a quote from Neil deGrasse Tyson, but he's totally right on us. You know, when you look at us, our closest relatives, chimpanzees, you know, if you go back 6 million years ago, we had a common ancestor. It was neither a human or a chimpanzee. It was a creature about this big. And some of these went these way and became the chimps, and some of them went our way and became the humans and other species that led up to us. And you know, I forgot what my point was on that one. But the difference in intelligence. So the difference between, you know, the intelligence between us and a chimp, the DNA is only 1.7 difference. But what if we come to a creature that's that much smarter than us in that difference? What if they're twice as smart as us? What if they're 10 times? I mean, we're trying to figure out the universe, what happened, what created the universe. We might not be smart enough to understand it, you know? But then you come across another being, you know, they're teaching their fourth grader, you know, Dad, I figured out the universe, you know? You just don't know.
That's right. And, you know, they always say like you're searching planets, okay? That there is life out there because they've discovered millions of planets in the solar system or in, you know, in the galaxy. That have temperatures like ours or could support life, but that's only life as we know it anyway.
And it better have better have the right amount of oxygen and all that.
It could be a totally different kind of life that we don't even understand.
Oh yeah, yeah. I mean, we have 2 arms, 2 legs. That's because of one animal that one species that we're all part of. If that species died off, we would have died off, and who knows what the life would be. You could have, you know, who knows what the life could look like.
That's true.
You know. I mean, we're all related to, you know, one animal. Go back far enough, you know. If you go back far enough, we're related to oak trees, you know. You know. All right, any other questions? No. Okay. Well, thanks for coming. I hope you enjoyed it. Thank you very much. Thanks.